Alright, welcome back. This is going to be the final video in which I present inductive proofs for recurrence relations. And the recurrence relation that I've selected here today is one related to the merge sort algorithm. It's sort of a lower bound on the merge sort algorithm, but we're going to prove upper and lower bounds for this recurrence relation so that we can practice induction with recurrence relations. Okay, so again, I've got this started out here. In a previous video, we came up with a guess here for this recurrence relation, and the guess was n log n. And so I want to prove an upper bound to start out. That's going to be our big O of n log n here. And we're going to do that with, again, an inductive theorem here, just saying t of n is less than or equal to b times n log n. I've crafted this theorem by selecting this b times n log n function out of my class of big O of n log n. It might not be the best function to use, but let's see here in a second if it's going to work out for us. I'm going to start here with my base case. I've decided to do n equals 1. Here t of 1 is just a constant, and we need to show that this is less than or equal to b times 1 times log of 1. Let me make these ones a little bit clearer. This is 1 log 1. Well, log 1 is 0, so this whole thing just becomes 0. Now remember, this caused us problems before because c is not less than or equal to 0. In fact, the only thing we know about c is c is greater than 0. It's a positive constant. So immediately out of the gates, we fail. We've run into problems. And the reason we've run into problems is the same reason we had earlier when we looked at binary search, is this log. The log is causing us problems. When we plug in our 1 into the log, it gives us a 0, and the 0 cancels everything out, nullifies our b, and makes it impossible for us to make this true. So I'm going to show another trick here. When we were dealing with binary search, we moved our base case. We said, well, 1 didn't work, let's do 2 and 3. And that's a good trick. But here what I'm going to do is I'm going to use another technique, which is I'm just going to change the function that I'm trying to prove. I'm going to put a plus a on here. Let's see why this one works. Now, I'm going to say t of 1 is c. And again, now what do I want to show it's less than or equal to? I want to show it's less than or equal to b 1 log 1 again, so that's still the same. But now we have this plus a. This gives us an extra degree of freedom. Remember, we get to pick a as well. It's another constant we get to pick. So when the first bit becomes 0, we still get a. So the condition we have here is as long as we pick an a that's greater than or equal to c, this works. And now we don't need to expand our base case to 2 and 3. However, we've added this extra little bit. Let's see how that impacts now our inductive hypothesis. Okay, we see here that when we copy down the theorem we want to prove in our inductive hypothesis, as we've been doing, but rewriting it in terms of k, we have to keep in mind that this plus a does come down as well. We don't lose it. We don't just use it for our base case and then ignore it. It has to be there for the entire proof. That's actually going to impact our inductive step as well, because when we have to prove our inductive step, we still need to use the a is going to show up here as well. Okay, so even though we've added it up here just to help with the base case, it's now introduced itself into our inductive hypothesis, and which is good actually, because we're going to need it later on in our inductive step. Okay, so let's once again carry out our inductive step by, well, the first step we did here already by writing down the definition. So the second step is to apply our inductive hypothesis. Again, when it gets a little tricky like this, we might want to say, well, what is t of the floor of n over 2 really going to be less than or equal to? We get to approximate it out here. It's going to be less than or equal to, it looks like b floor of n over 2 log of the floor of n over 2 plus a. So that's actually a kind of messy little piece. That's what we're going to put in here, keeping in mind there were 2 of these terms. So we don't want to forget that. Don't forget the 2. And then we're copying in the right-hand side from over there. b times floor of n over 2 log floor of n over 2 plus a. plus dn. Okay, let's keep going then. And we get less than or equal to. I want to, I don't know, there's a couple things we could do here. I'm actually going to do two at once, save ourselves a little bit of space here. I'm going to cancel out my floors, and I'm going to multiply my 2 in. So that first 2 is going to cancel with this 2 here after the floor is gone, leaving us with just bn, still multiplied by this term, log, well, I said I'd get rid of the floors, so let's get rid of them. Log of n over 2, plus, now be careful, the 2a here, 2a plus dn. Okay, it's a little tricky. We kind of want to get something to cancel out with this. We don't have that yet, but luckily, hopefully, if we simplify this log, we'll get there. So this is actually going to be bn log n. Hey, that's the term we're looking for. Good. Minus bn. Okay, the log 2 that we get in the minus there is just 1, so we get minus a bn plus 2a plus dn. Now that's kind of looking like what I want, but I'm going to rewrite it to be very clear. We have our bn log n term. We actually also have our plus a term. I'm going to split one of my a's out of there. And then I'm going to have, well, let's maybe write that other plus a minus bn plus dn, because we got these n's over here as well. Now this bit is what we want to keep. So this bit is the stuff we need to cancel out. Now if we want this last line, our leap of faith, to be true, then we need this extra bit here to be what? Less than or equal to 0. So we want a minus bn plus dn to be less than or equal to 0. And we did this last time. We got a plus dn is less than or equal to bn. That's just by moving our bn to the other side here. And then again with transitivity, if we promote this to an, that's not a sub n, sorry, that's a times n. By transitivity, we get this is true. So here we're just going to cancel out our n's, and it looks like our b must be greater than or equal to a plus d. Oh, that's a little bit problematic. We don't get to pick. We don't get to pick what these values are. Sorry, we don't get to pick what d is. That's already given to us. We get to pick what a and b are. So we should probably solve this in terms of a and b. So I'm going to rewrite this. I'm just going to move my a to the other side. I'm going to say b minus a must be greater than or equal to d. Okay, that's the condition I found over here. This was another condition I found over here. But now we have two variables. So I'm going to say let a be c. A only has one condition up here. And then b is dependent on a and d. So I'm going to say, why don't we let b be equal to, let's see, we could translate this if we really need to. We actually already had it up here. B is greater than or equal to a plus d. So our a is c. So why don't we make this c plus d? And then we can say, so t of n is less than or equal to b times n log n, not that, but plus a for all n greater than or equal to, well, we started at n equals 1, so we proved this true for all values of n equals 1 or greater. Okay, again, I just want to highlight here, probably the key thing I want to look at here is to handle the base case that that didn't work for our log, we added this plus a on here instead of expanding our base case to 2 and 3. That plus a trickled through our whole proof. It showed up everywhere, but at the end it allowed us to show this was true for all n greater than or equal to 1, whereas if we had expanded our base case instead, we would have only shown this was true for all n greater than or equal to 2. Now the difference between those is not very much. They both establish the big O bound that we want, and so they're both acceptable. Both techniques are good techniques for coming up with these bounds. Okay, now I want to complete this with a final look at just the bounds, the lower bound, I guess, the big omega bound for the same recurrence relation. All right, we established that our recurrence relation for the merge sort algorithm was in big O of n log n. Now I want to establish that it is in big omega of n log n, again using an inductive proof. So we want to show that t of n is greater than or equal to a times n log n. Let's again start with our first case where t of 1 we know again to be c. And we need to show that this is greater than or equal to a times 1 log 1, which we know to be 0. So remember, this is true for all values of a because we know c is greater than or equal to b 0. So let's head on to our inductive hypothesis. Okay, so in our inductive hypothesis, once again, we'll just copy down what we're trying to prove. So we've got t of k is greater than or equal to a times k log k. And again, for restricted values of k, for k less than n. Okay, proceeding to the inductive step. All right, in our inductive step, we'll start with our definition, and then we again want to apply our inductive hypothesis. So maybe on the side, for a final time, I'll make a little scratch here. T of the floor of n over 2, that's the term we want to replace. What is it greater than or equal to? A, it looks like plugging in for n over 2 here. We get a floor of n over 2 log the floor of n over 2. So again, remembering the 2 is there, we're going to replace that here with a, the floor of n over 2 log the floor of n over 2 plus dn. This is actually the point. This is going to be the trickiest of the induction proofs we're probably going to see here, because now I want to get rid of my floors. And on the upper bound it was easy, we just ignored them, but on the lower bound we've got a couple cases here. We've got floor of n over 2. Sometimes we say that's greater than or equal to n over 2 minus 1. And then in the previous video, I think we also used the approximation here where the floor of n over 2 is greater than or equal to n over 4 if n is greater than or equal to 2. And that happens to be the case that we're in. I guess I didn't state here, but we're in n greater than 1 for our inductive step. So indeed, we're in the integer realm. That means we satisfy this condition. So we could use either of these approximations to get rid of our floors, and it turns out we actually want to use both. If we don't use both, we're going to cause a problem. I'm just going to multiply my 2 in for a second. We're going to have 2a. Now this first one, the one that's outside the log, I want to do the closest approximation I can to it, which is this one here. So I'm going to do n over 2 minus 1 on the outside. Now inside the log, that minus 1 usually causes us problems. So inside the log, I'm going to make it a 4, an n over 4. Okay, plus my dn. Let's see where that gets us then. Let's try and multiply things out. So let's do the first term here. The 2 and the 2 are going to cancel, so we get an a n multiplied by our log n over 4. Then we get a minus term here. It gets looks like it's a minus 2a log n over 4 plus dn. Okay, let's be careful again. I'm going to now handle both my n's over my log of n over 4. So remember our log identity. Maybe I'll make a little extra room here. My log identity, my first one's going to be an log n minus an, I'll be careful here, log 4, which is just going to be a 2. We'll cancel that out in a second. The next one here is going to be minus 2a log n. Minus a minus is a plus, 2a log 4. Again, just going to be a 2 in a second. plus dn. So let's just say this is a 2, this is a 2, and we actually have our term we want. So remember, we're trying to say that this is greater than or equal to n log n. And then we got a bunch of extra stuff. So let's see what our extra stuff is going to be here. We've got minus 2an. We've got minus 2a log n. We've got plus 2a. And we have plus dn. Okay, and we want this all to be greater than or equal to, sorry, this line was actually just algebra that I just simplified, so I'm going to replace that with a equal to. But we want this whole last thing to be greater than or equal to a n log n. And remember, this step is what I've been calling my leap of faith. Okay, we just hope it's true. Well, we don't really hope it's true. We want to know when it's true by looking at all this business and figuring it out. Well, we want all this business to either be greater than or equal to 2. Or sorry, greater than or equal to 0. We want it to be either positive or 0. So we're going to have minus 2a, and I'm just rewriting it here, minus 2a log n plus 2a plus dn. And we want this to be greater than or equal to 0. Again, I want to make sure, looking at all my terms, that I could even make this canceling out. Do I have enough positive stuff to cancel out this negative stuff? Yes, it actually does. I've got an n term here that's bigger than a log n term, and it's the same as an n term. So hopefully with some good choices of my value of a here, I can make this cancel out. So again, I'm going to just do a little algebra on the side here to make sure we get it right. 2a plus dn needs to be greater than or equal to, moving both those to the other side here, we have 2an plus 2a log n. And now here again, we need to be careful to know which tool we want to use. The tool I'm going to use here to get rid of this log, okay, and so again, we want our 2a plus dn to be bigger than or equal to all this business going on the right hand side here. Okay, we want this 2a plus dn to be bigger than or equal to all that's going on the right hand side. Now one thing I'm going to try here, here's a technique. What happens if I made this one bigger? What happens if I promoted my log n to n? That makes the whole thing bigger. So again, by transitivity, what I want is this. Okay, remember, what I want is this. But if I can show this first one, which seems like it might be a little bit easier, then I can get that by transitivity. I'm going to go one step further. I'm going to say, look, if I could just show that if I could just show that this dn by itself is greater than this here, then the dn plus the 2a must be greater than this. So again, I'll move my scratch up here. The final thing I want is dn must be greater than or equal to 4an. And that one I can easily calculate. Cancel out my n's on both sides. It looks like my a needs to be less than or equal to d over 4. Okay, so looks like we've really filled up, including our scratch here. So maybe let's go down here. So, let's scroll down a little bit. So, what should we do? Let a be equal to, and what were our choice? Any a in the base case, or what did we get here? D over 4. So let's say d over 4. Then t of n we've shown is greater than or equal to a times n log n for what values of n? N greater than or equal to 1. Okay, so the d here. So again, in this proof, we've mostly used all the same techniques that we've already seen before. The only key here is, even though we've seen these two techniques here before, in approximating away these floors, we needed to use both of our approximations. If we didn't, everything doesn't cancel out the way that nicely that we do here. We might give away too much in our approximation. And so if we didn't do it this way, we wouldn't get the nice algebra settling out. So again, this is just meant to be practice, to show us, hey, with a lot of practice, we'll encounter all these different tricks. Some of these are tricks we've seen before. So it just with a little bit more practice, if you encounter any of these problems in your own work, then hopefully you'll be able to very quickly demonstrate to yourself or to your other coworkers that this is indeed the runtime bound for your problem or your algorithm. Okay, so this concludes my discussion of the runtime of merge sort and our discussion of using induction for finding bounds or proving type bounds on recurrence relations. So hopefully we've got lots of good examples of how to do that now. But in my next video, I want to, again, we will still be practicing and working with these same techniques, but I want to pivot and approach the quicksort algorithm. And I will do that by looking at actually two variants of it, the deterministic quicksort algorithm and the randomized quicksort algorithm. All right, thank you for watching this video, and we'll see you in the next video.